So Animesh is an assistant professor at University of Toronto. He also works with Vector Institute and NVIDIA. He has won multiple, best paper awards. His work has been widely covered in the press. And of course, he was at Berkeley, before going off to Toronto. So, with that, Animesh, super excited to hear your talk and looking forward. Please take it away.
Thank you, Pulkit, and thank you, Avi, for inviting me, and thank you, everyone, for showing up. Thank you for the privilege of your time. I am Animesh, and I am currently actually still in Berkeley, physically, and it's been wonderful and weird conducting research in the last few years on a lot of these interesting topics, particularly in robotics, where robots have been hard to get to. Which has actually forced me to think about 4 questions in understanding of building decision-making systems for robots. So what I'm going to hopefully discuss today, or at least try to discuss as many points as we can touch on, is what I believe could be the missing blocks or missing building blocks in our quest for generalizable autonomy. So I'd like to start here. This is something that that a lot of science fiction folks love. This is, of course, a video of Rosie, the robot, doing everything out of home. And this is what I like to call out-of-the-box autonomy. This is something that, this video itself is fairly old, but the problem, I feel, is evergreen. As a roboticist, I believe I would love to build something like this. And now, of course, the problem of generalization appears, where we would want something like this to not only do one task, but hopefully do a variety of tasks: vacuuming, cooking, cleaning, sweeping, laundry, so on and so forth. And even more importantly, it needs to work with the diversity of scenes, tools, objects. Perhaps I forgot to do laundry, and it should be able to do harder tasks than it was shown before, or you have a child at home, cleanup should be harder, so on and so forth. But I think the whole point is that it needs to, or the system that we are trying to build needs to be able to not only work in control settings, but extend to diverse and complex situations. Now, of course, it's not that we haven't built impressive hardware systems. This is a video again from Boston Dynamics. All of the roboticists like to sort of pick on Boston Dynamics despite their impressive work. The video is actually their Christmas greetings, about 8 weeks old, where the robots are doing perfectly wonderful things. But the only catch is that all of this sort of video is choreographed. The whole thing is known structured environments. And now you take the same robot, you put it in some sort of unstructured environment, and the thing kind of falls up. And the question basically is, what is missing? And I would argue the missing component is algorithmic generalization, and where the component of generalization or definition of generalization, I'll probably clarify later on. But for now, it's sufficient to understand maybe generalization is through notion of objects, scenes, semantics, perhaps even goals. So overall, what we want to do is to understand what sort of blocks or what sort of components do we need to achieve this sort of generalization. I believe that a system to achieve practical use cases will consist of at least 2 components. One is this idea of task specification. We need to specify tasks. The specification of task itself can happen through a variety of supervision inputs, maybe language, videos, or maybe handholding in the sense that you give demonstrations to robots kinesthetically. And then we need algorithmic mechanisms where we can take these task specifications and generalize them conceptually, semantically to new task environments or variations under new constraints. So now let's step back for a minute and understand what is going on in the last 5 to 7 years in machine learning before we jump back to robotics. I would argue a lot of progress has been made, particularly in our sister fields in machine learning, say computer vision, language, or speech recognition. And you could sort of argue that these progresses have been built on 3 or 4 core ideas. One, there were better models. Perhaps they were over parameterized. They had better structured biases. Number 2, large data sets. It's not only that there were large data sets, the problem definition was almost always concise. Image in, token out, right? And then because of the concision of the problem, or problem specification, you can label or collect data at scale. Similarly, the data that you're collecting implicitly assumes independence. So it assumes that all of the data that you're collecting is essentially IID. And finally, there is availability and a mechanism or framework to do compute and deployment. You can have large-scale compute and distributed deployment. Now let's go back to robotics. To think about robotics, it turns out none of these things are actually true. If you think of models, whether machine learning or not, models aren't very complicated. We are probably using 3-layer neural networks. Data sets are at least 3 orders of magnitude smaller than vision and language. Data is almost never IID. And compute and deployment is, compute is available, but data is not. And deployment is actually very unstructured. So what you run in your lab may not be available or may not be workable in mine or the other way around. So it's not fairly easy to generalize. Now, of course, robots appear in, well, many forms, shapes, and use cases. Over the years, I've worked on surgical robots, service and manufacturing robots with manipulation. And lately, we have also been looking at locomotion. And a lot of the problems we work on are both motivated by and are applied to in these domains. But the point here is that there is no sort of singular system to look at all of these problems in one go. So what I'm going to do today is to think about how we can build towards this more complicated practical systems in robots and how we can think about what will be deployed. So we'll need to start with understanding what are the true building blocks in decision-making systems? What sort of structured biases matter? How can we put these structured biases together, perhaps into more useful structure discovery, like causal structure discovery? Then we'll talk about, now that you have the data, or perhaps you have the data and maybe even some algorithms, how do you even think about building practical systems that are deployable? And then, oops, there was some error. Then I'll probably, if time permits, discuss some open questions that I'm looking into. So let's start with inductive biases. So let's go to paradigm that seems very common at this time. You have a robot, you want it to do something very simple. Let's say it's a simple path following on a table. Of course, this task could be much more complicated. You have some sort of sensor. In this case, we have a camera. And then if we look at more recent mechanisms of attempting this problem or the end-to-end version of this problem, we would more likely not model it as an MDP, which is basically a core object in reinforcement learning. What the objective of this problem is to find a mapping from states, which can be images, robot proprioception, or some other input, to some sort of actions, maybe torques or some sort of mechanism or an API that you control the robot with, such that you optimize certain reward model. Now, this is what a current model may look like. You have state inputs. There is some sort of policy. If policy is represented by a neural network, then it may be 2, 3, 4 layer deep neural network. And it outputs, let's say, torque, something simple into it. Now, of course, the system can be thought of as essentially an environment and an agent kind of setup. The question really is, where is this structure? Where should the structure be? And what is the structure that we are leaving out? And I argue that if you look at this framework, there is a state input, there is an output in action space, there is policy, and then there is a learning rule itself. We are leaving a lot of structure on the table by using something very simple. When we think of states, if we push in images, perhaps through CNNs, and then directly through some decision-making system. Similarly, when we think about control, we have the robot or the system output maybe torques, and then hopefully expect it to work. Similarly, when we think of policy, we have these simple mechanisms, which are, well, function approximators, but very simple nonetheless. And then learning rules. Learning rules, in this case, it's a simple Q learning. Of course, you can have different learning rules, but learning rules aren't very complicated and are not necessarily representative of the real problems. One example can be all of these learning rules that we actually apply are built for infinite horizon, but we basically indiscriminately apply them on finite horizon problems and pray to God that it works. So it does sometimes, but it isn't always correct. So let's start with state first. So let's say we look at a task, maybe something that is a task that requires you to do both visual and tactile sensing. So maybe plugging in electrical plugs. It requires both alignment and insertion. And then, of course, you don't want to do just this one instance of the task. You probably want to do this family of tasks, maybe keys or bulbs or so on and so forth. Now, if you were to think about how a controller would be built, you could argue that you have some sort of inputs, maybe let's say images and touch. This could be converted into some task relevant information. Let's say poses, some sort of physics properties of the scene or of the task. And then you can build a controller or a policy. And usually the policy would look something like this: observations in, torque out. The first instance of structure that we argue we should start thinking about is how should we map observations such that policy doesn't have to do a lot? Can we map observations in this particular case into a more generalizable, usable representation? So the idea was that let's try to separate what goes into the policy into first a function that is a multimodal representation of inputs, and then policy in this representation space. So we start with this task where we have a peg insertion task. Of course, it's a fairly simple task, but the interesting thing is we have three inputs: images, force torque sensing, and then of course the robot state. And then the setup is such that the setup may have peg shapes and holes of different shapes. The robot does not know, there's nothing in the state that tells what is the actual shape of the peg, except for maybe the image. So far, so good. Any questions so far? Cool. So now what we did is we basically looked at, can we learn a state representation that can encode all of these multimodal inputs into a single representation? So we have three modalities of input. We can encode this input into a fused representation, and then decode to some specific task relevant labels. But that actually can be very expensive because we don't actually have this task relevant data or supervision. So what we decided instead is to come up with a mechanism of self-supervised learning, where you can have data collection through either random perturbations or where data streams are correctly aligned. And the fact that we have this data itself gives it labels. So in this case, what you see is optical flow, normalized forces, and images from robots viewpoint. So now what we can do is we can build an encoder where we are basically asking it to predict first action conditional optical flow. Second, just a simple binary label of is there going to be contact in next step. And finally, if you jumble inputs, you should be able to tell that inputs are not actually correct. So you could basically say that this representation learns some sort of cross-modal filling or predictions, so that in case one of the input modalities is corrupted, the representation would still be robust. The interesting part here is that majority of the learning happens in this representation part. The policy part of it is actually fairly lightweight. So maybe about 3% of the whole learning scheme. So let me directly jump to the result of what this gives us. We can take this schema, train the model, train the representation, and then train an RL policy directly on the row. Here, the policy is not trained in simulation. Nothing is done a priori. The whole thing, the whole data pipeline is on a real row. The policy takes about 3 to 4 hours to train. Let me play this again. And in this case, again, there is no tracking of the target, and nothing in the environment is, let's say, motion captured. So with image-based models, the policy can figure out how to do this sort of insertion task. So just to go back to more numerical results, we looked at different tasks for different shapes and success rates for those tasks. We actually also did something very fundamental. Basically, the value of different information, which is not very surprising, I would argue, that as you add more modalities, success. But more interestingly, what we tried out was, if you train and test the policy, the representation and the policy on the same shape, of course it works. But if you swap the testing setup, but don't retrain the policy, it starts to fail. On the contrary, if you keep the representation from some other shape, but only retrain the policy, then it actually works. It's the representation that transfers, policy does not necessarily transfer. So broadly, just to recap, we are able to collect about an hour or two of data. It takes about a day at the time. This is about 2.5 years ago to train this representation. And then the policy learning part takes about 3 to 4 hours, or maybe 5, depending on the shape, actually, to train a policy. But the big picture idea here was that it's the policy that transfers, not necessarily, the representation that transfers, not necessarily the policy. The representation is the structure that you can have in the input. It can be trained once for a task domain rather than for every task. And then policy is actually fairly lightweight to do. So this was the part where we looked at state. So we were looking at state here. Let's look at the other side of the system. What about actions? Actions is a bit more interesting, actually. So if we were to do, let's say, a simple task of wiping a table, same task that we thought about, how would we think about this? We might build a model of the robot, maybe a kinematics and dynamics model. And then we'll have to write some sort of behavior tree or a task model. So you have to go to the table, then wipe, and then you have to change the gains as you go along. And then any sort of task in this setup or in this regime will have to have some sort of explicit state estimation or task-dependent state estimation, at least, if not explicit. And of course, this works very well in a number of use cases. It's compliant. It allows us to use the robot model. But it does require a lot of information about the task. Now, of course, our favorite deep RL model allows us to bypass all of this just to do whole thing in an end-to-end fashion. But the question usually is that how robust is that? How efficient is it? And would it transfer across domains? So one thing we really thought about is maybe perhaps we should start thinking about where or in what space are we doing reinforcement learning in? What is the best of both worlds? One way to start thinking about this is, now think of a mapping outside the policy. So earlier, just to remind you, we were looking at a representation that transformed the input before it went into the policy. Now we are transforming the output of the policy into something that would be easier for the policy to explore, but at the same time allows us to leverage our knowledge of the system. So one way to think about this can be to think of task spaces. So one task space is end effector task space. So we can allow the robot to operate in end effectors. Of course, that would be an easy task space. A more interesting version was to actually allow the policy to also set gains in the task space itself. So what basically you are saying is, not only is the policy operating in, let's say, delta pose space of in task or pose velocity, but you are also able to set gains in this space. So when you touch the table, you don't have to change gains or change mode. The policy will automatically figure out that the stage of the task has changed. And this is something that allows it to do more interactive contact-based tasks. And overall, of course, this allows us to be model-free. I don't need to model the environment or the task in stages. I can learn essentially compliant control, or at least the compliance can be inbuilt into the model. And it will be sample efficient and transferable, as I'll talk about. So on a very simple task, again, wiping task, in the inset is the figure that, or the image that the robot actually sees. And we compare a number of different action-space modalities in which the policy can operate. Without getting into all of the details, the thing to sort of take away here is if you operate purely in torque space, after about 1 million time steps, vices or variable impedance action space has basically solved the task while joint torques are still learning. And all of the other models are kind of in between. The more interesting version was, because of the way we were able to separate out the policy from the robot model, I can now train on Panda and try to change the outer model. So let's take a Sawyer instead and swap the model. Of course, there's loss of performance, but the policy does perform out of the box. So again, the fact that you have structure in this representation, the policy somewhat transfers. Even more interestingly, I can do the same with sim to real. Now I don't have to do randomization or any sort of funny business here. I can actually just train very simply in simulation and swap with a real robot model. What are the things that I may be swapping? Maybe my kinematic structure was not exact, or my inverse dynamics was not exact, depending on what my system ID was. And in this case, that's what we saw. And the robot in the real setup was about 80% successful, even on image-based tasks. Now, this framework, by the way, of operating in correct task spaces is not just limited to manipulation. We tried this also on legged robotics. So think of a legged robot. Instead of doing end-to-end training for control, you can start thinking of the robot in some abstract task space, maybe only the torso, and then the legs. The pipeline of the system can be that a policy only needs to operate on body accelerations and angular accelerations, while a QP solver can come up with ground reaction forces for every foot. And then depending on what model you're operating with, whether it's like a Go or A1 or a different robot or sim or real, you can take the same policy over and over again. So we actually were able to do that very recently, where you can train on the standard like a Go, flip the legs, and it still works. You can take the same policy and apply it to a different robot, or even apply it to a real robot. With that, again, without too much randomization or any funny business. So the key idea here is, again, that if you think about learning in the right structured spaces, you can get both efficiency and generalization. Now, of course, we are machine learning people sometimes. So a lot of people, including myself, are thinking, okay, in this case, we injected a lot of structure in the setup. Task spaces in both of these cases, both the manipulation and the legged robot case, was something where I had known about the task space beforehand. I was just checking, will RL succeed in this task? So let's see if we can learn this task space. So first of all, let's look at why would such a learning setup even be possible. So think of a very simple task, maybe opening a door. You can open a door in many use cases. Maybe some of the doors open to 45 degrees, some of the doors open to 90 degrees. Doors have different, let's say, stiffnesses, maybe geometries. But if you really think about the implicit manifold of the motion that you have, it's not very high dimensional. Definitely not full 6 dimensional, or it's actually 18 if you think about all of your tuning gates. It's actually much lower dimension. So if you look at the family of tasks, different tasks in this domain, you should in principle be able to learn a much lower dimension compact representation of this manifold so that you can only travel on this manifold what would this be similar to? This would be similar to saying that when you are trying to open a new door that you have never seen before, you only try to open it in ways which you believe the door will open. You never sort of yank it vertically, because you know that there is very little reward to be had in that space. So we need to learn some sort of action space here, which is conditioned on state and actions, controllable in the sense that I should be able to operate in this latent space, but there's a mapping to the real robot. Consistent in the sense that if I basically apply the same latent space, same latent control, it should basically have the same local effect. So it's locally consistent and scalable. So it's if I apply a multiple of action in latent space, then the same sort of effect scales, perhaps non-linearly, but ideally in a similar manner. So this model can actually be learned as a VAE, but with certain constraints. So the standard VAE can be set up as action and state in and action representations out. But there are a couple of other, let's say, constraints. One is states are actually also converted into some state representation. In this case, it's a simple MLP, but you want to make sure that the prediction is dynamically consistent. So you make sure that the latent space is dynamically consistent. So this is enforcing equivariance, if you will. Does everybody, any questions so far? If not, let's carry on. So now this kind of setup can be trained usually, as we do with VAEs, in an offline setup, in the sense you collect a lot of data, then you train the model. Once you train the model, you can use the representation. But interestingly, you can do this iteratively while you are learning the policy itself. So you don't need expert data necessarily. Let's look at what this does. So directly, I will jump to results and I'll show you numerical results later. So what we see here is offline laser means you collected a lot of data and then trained a representation and then trained RL on this representation. Okay. So when you start training or with PPO, nothing much really happens. But notice that laser policy already has the right action space where even random actions can actually result in a reward. Of course, after, well, 8 million training steps, PPO does figure it out, and so does offline laser. So what is happening? Yeah, question.
A quick question. So is
Yes.
when you're having this abstract action space, do you have a fixed number of actions per Z, or is that variable?
Fixed number of actions per Z. Well, the Z dimension is fixed, but not the actual map.
So the number of time steps could be variable depending
Oh,
on the
this
Z
is not in time steps. This is very important. So this is not a temporal. This is not a temporal map. This is actually a spatial map. So you can really think of it like that. So yes, the temporal version of this, we also have papers on that I'll probably not get a chance to talk about. But this was actually looking at if you're talking about opening doors, you should in principle only have one dimension, which is T of the curve. Of course, you don't actually are able to reduce it to one, but you can implicitly learn the right tangent space of the manifold.
Okay.
So what you see here is basically training of laser space in both of these sort of task spaces. But the interesting thing is SAC baseline, or which is basically the RL baseline, takes forever to sort of catch up. And x-axis is actually non-trivial here. It's multiple millions. But the laser baseline is working from basically off the bat. Why? Because it has learned the right manifold, and even random actions in that space actually do result in correct policies or correct outputs. Okay, so let's continue. So you might say, we collected demos, we learned this action space, does this work? I would argue, yes, at least this part on the same task, it does work. But then there's not much point if it doesn't really generalize. If you have memorized the solution from the experts, what's the point? So does it generalize to different tasks in the same task family. So in the door environment, I train it to, let's say, open the door to 30 degrees and then test it on every other end, right? So that's what we do. So we transfer the task on a different task. So maybe 30 to 60, 30 to 90. And yet again, we see that because the tangent space of this task domain is all the same, it works off the box. Now, well, of course, you can say, but you already know the solutions that collected the data. Can you do this when you don't actually have the experience? Turns out, yes, you can actually learn the representation online in an iterative fashion as well without loss of learning performance. So you can still learn the representation that will generalize, but while learning the task itself from scratch without any prior information or data. So you can do this both in offline setups and in online settings. Then what we can do is, yet again, I can show you here, is not only does this result in successful solutions that generalize, they are also more natural because of the fact that that you are enforcing this representation to be the tangent space that generalizes to a variety of use cases. If the data is coming from a number of tasks, then the solution does look a bit more natural rather than trying to find holes in your simulator to open the door. I only talked about one simple example, which was the door opening example. But this idea, we tried it on a number of tasks, block pushing and wiping tasks as well. So interestingly, now, aside from RL, is this idea useful? So we actually tried this on assistive teleoperation. So this was our VAE model where we are trying to train this model on some task. And we are trying to see if the whole system is useful. But now, what is to stop us from changing the input from a policy to a human? So now what we are going to do is we are going to collect data in an offline setup. We are going to train the system such that you can have a very low dimensional representation to control a high dimensional object. So a 2-dimensional representation to control a 6th of R. And what we were able to do here is, of course, that in this kind of setup, you can do pick and place tasks with very simple input commands. And then this is also both efficient from a user's perspective in terms of time, and the users find it very easy to use as well. The more interesting part of the thing to note here is there is no free lunch. So no free lunch argument is you cannot learn all of the space into 2 dimensions. It only works if there is a task manifold, and task manifolds usually do exist for task families. If you want to capture all of the places that the arm can go to, the full workspace, probably not very useful. But that's the whole intuition here, is that many tasks implicitly have a manifold over which you need to move around rather than moving in all possible positions in the workspace. Okay. I have about 20 minutes or so. One more very interesting result. I'll probably not be able to get into a lot of details of all of the results. When we think about reinforcement learning, particularly deep reinforcement learning, it's not very deep, actually. It's maybe 1, 2, or 3 layers. And then the question we are asking is, why not? Why not just sort of add more layers to the model and what happens? It turns out that because of the way the policies are structured, you cannot just keep adding layers because there's a loss of information. So the representations are incrementally lossy. And because they are incrementally lossy, to do policy learning becomes increasingly challenging. And for the kinds of tasks people are looking at, for example, simple Mujoko tasks, it turns out that 2 or 3 layers were actually the optimal ones. So we started thinking about what are ideas our friends in vision are using. One of the things that people in vision very frequently use is this idea of residual connections or dense connections, which is basically saying that keep old representations or earlier representations around while starting to compress representations. So you are basically saying that with every transformation, I get a new representation, but this new representation may not be sufficient. Hence, I will keep the old representation around, which is this dense connection idea. Right? So it's basically increasing the basis function of your vectors, if you will. Surprisingly, A very simple technique like this improves performance across the board, across tasks, across algorithms. This was so surprising to us that something as simple worked. So we tried on OpenAI Gym with TV3 and SSE. We tried on more difficult robotic environments. And the more difficult the task, the more sort of value of doing this. So JCO Reach or Ant Maze or sort of the takeaway here was, it's not necessarily that this is the final solution, but it is definitely a pointer that the models that we are using for deep reinforcement learning are definitely very primitive. We haven't thought about what sort of structural biases we can induce in the policy itself. So when we think about decision making, we should start thinking about what are the key differences or key properties or characteristics that we need in decision making, and what are the invariances that we need. So just as people in vision thought about invariances to visual input data, in decision making, we might want to think about working memory, ideas of attention, ideas of memory to begin. And those are the kinds of structures that we might want to include in our policy architecture itself. I will not get a chance to talk about the learning route today, but happy to chat about this later. Broadly, by the way, this idea of structure becomes equally more important or sort of even more evident if you are starting to think about longer horizon tasks, when you start to think about tasks which require planning rather than just control. And for these, we have also looked into structured representations such as hierarchical latent variable models for dynamics. We have also looked at thinking about decision-making problems as neural program synthesis problems or program induction problems, where you can model the planning problem as essentially predicting a sequence. You can think of the program itself as a graph, an implicit graph, if you will, where achieving a goal is essentially finding all pair shortest path. So you're just planning in this implicit graph of abstract symbols and actions. So far we discussed this idea of where would we have structured inductive biases and what sort of inductive biases would matter. But now let's think about if we have data, or if we had data, what would we do? So one of the things that we did note is as the complexity of the tasks that we want to achieve grows, so from skills to planning to structure, the data sets, particularly in robotics, start to shrink very quickly. Now, if you want to really achieve, let's say, some sort of execution, procedural execution by watching a YouTube video, say, we need to really think about where are we going to get larger sets of structured supervision. We know from a number of works in the community that imitation learning or learning from data, even in robotics, works very well. It allows us to perform tasks which may not be possible with pure RL, regardless of compute. But if you look at the data set sizes in these examples, they are actually maybe of the order of half an hour worth of data. Now, of course, if you look at fields in vision or language or vision plus language, these data sets are much, much larger. But robot learning is basically yet to witness this success. And to unlock this success, we have to think about how are we going to get this data. So in the time that remains, about 15 minutes or so, I want to talk about some recent work, some very recent work on one, how do we collect data and learn from this data? Two, can we do better than just pure supervision or supervised learning? And then how and where causality can help. So the first thing we started looking at is this idea of implicit reinforcement or batch reinforcement, or also known as offline reinforcement at this point, where you have a lot of data and you want to learn a policy in a sandbox. So first up, we built a framework called RoboTurk. RoboTurk allows us to collect data both in real and simulated environments at scale through crowdsourcing. It only requires a phone app which is why it allows us to scale up data collection without asking users or data collectors to have any special, let's say, hardware such as VR or some sort of special tracking. Just to demo this, we actually collected data that was 10x larger. I think this was 2018 or early 2019. Since then, folks at DeepMind and other places have also collected equally large data sets. But at the same time, the problem of learning from these large data sets, particularly in reinforcement learning setting, still remains. Can we learn a robust and performant policy purely from these experiences? So just to recap, the setup is you have a large set of demonstrations and you have to do policy learning, but there is no interaction that is allowed. So it's not that people haven't worked on batch RL. There have been a lot of works on batch RL even up until very recently, but usually most data sets are coming with dense rewards and they are trained on either locomotion tasks or Atari games. And then for robot manipulation, usually the data is much more unstructured and the rewards are much more sparse. The problem, simply stated, is actually suboptimality and diversity, in the sense that there are many, many ways to fail and equally many ways to succeed. And when the data is so diverse and multimodal, any sort of learning algorithm can falter because of the inability to model the complexity of the data set. So one of the first algorithms that we came up with is an idea that has now become very popular in the field, actually, is the broad framework of using a high-level and a low-level model. The high-level model is a goal selection module, if you will, and the low-level model is a goal-conditioned follower module. So one way to think about this can be the high-level model is a state-to-state generative model. It is predicting states, looking at states. And then the low-level model only looks at the next state goal, maybe 1 or 2 seconds far out in the future, and then tries to come up with an action sequence that will achieve this goal in a closed loop sense. So I think that would be the overall setup. There's one more trick, of course, which is when you're selecting goals, it'll be probably easier for me to explain here. Okay, so when you're selecting goals, you sample potential future goals that are reachable, because this can be the distribution of the data you may have collected. But then, given the goal that you want to go to, you want to ensure that the goal that you select is actually aligned with what your final goal is, which is basically saying that you will pick from these samples a high value future state. So among these possible goals, you pick the one that results in bringing you closer to the final goal. And then now this goal state can be passed to a low-level goal condition imitation controller, which doesn't need to think about for what happens after this, just needs to figure out what sequence of actions it needs to take now. So just again, there's a generative model that captures the diversity of the data in the high-level goal model, and then the low-level goal model is only trying to do unimodal imitation. So that when you're doing supervised learning at the low level, you don't have the problem of a single input, which is mapped to two outputs. So we looked at a few different tasks, from very simple tasks such as just path following in a maze to block lifts and then pick in places. And what we found was that the iris model was able to achieve reasonably high success purely in simulation in simple tasks. And the trend actually repeats, but the numbers are albeit much lower in harder tasks such as go, pick, and place. More interestingly, you can do the whole thing purely from vision as well. So in this case, what we train is, on the data set, we train an unsupervised key point-based representation. I'm sorry that the video is a bit jumbled, it seems. We train a key point-based representation on this setup. And once the representation is trained, you can operate on just the key points as low-level states. This allows us to, again, train Iris, and we achieve a slightly better performance rate in this setup. So we have a visual sort of task that we can achieve in this setup. Qualitatively, we have a system now which can do goal condition imitation, which is critical to achieve learning in this diverse setup. Now, I want to jump to the next question. The question that we were able to answer with Iris was, large data sets are effective in batch or offline RL, and Iris was one algorithm that allows us to do this. So now the question we get to ask is, can we do better? Can we use the data more effectively? Which is where the next sort of effort that we did was counterfactual data augmentation comes in. So before we get into all of the details of how this works, let me give you an intuition. What is happening here? What is happening here is we are able to augment data in a manner that is dynamically feasible, even though that data point hasn't been seen before. So data augmentation per se has gotten a lot of attention in RL recently. So a few techniques which are very popular, or at least which achieved very, very high results, were HER, or hindsight experience replay, and randomized perturbations in visual data. And in both of those cases, the algorithms were surprisingly effective, even though very simple. So first of all, what we looked into is figure out, is there a unifying mechanism or unifying formalism for all of these data augmentation methods? So if you think of goal relabeling or HER, it's basically just one particular node that you are relabeling in the dataset, while visual data augmentation is akin to changing the states. So generically, if you think about a unified framework, if you think of state actions and goals mapping to future state actions and goals, you can take any of these nodes and remap them to a different node counterfactually. Counterfactually means that you have already seen data and you are changing some parameters or some values in the data. Why is this even possible, first of all? So let's look at a very simple example. So let's look at this simple example of pool. So you have two balls that are in this pool table. And what you see here is two particular time snapshots. Now, the question that I'm asking you is this a viable data point? What about this one? You could argue that the first one, or one on the right, is actually viable because you can take a compositional setup. So you can take the blue ball from the left and the orange ball from the right. While the bottom left one is actually not viable because I cannot guarantee say that what happens when they interact, because I've never seen them interact. So the same goes with your hands. You can have a bimanual system where if two arms are operating independently, you can make them, you can augment the data independently without worrying about the other. But when they do interact, you cannot do that. So what you're basically saying is, if you can figure out when objects interact in the environment, they depend on each other, then that new data point, which is compositionally generated, may not be viable, while at other times it may be viable. So how do we think about this? We can think about this from a perspective of local causal models. So truly, the global model may be dependent, but locally in terms of time, these objects or these entities may be independent. So this is a local causal graph, which is cliques which are separated. How do we find such cliques? So one way to think about this is, think about the same two balls. Whenever they are non-interacting, then the Jacobian of those matrices will actually be separable or independent, block diagonal in this particular case. This allows you to identify essentially the Granger causality, or the sequence to sequence mapping, where some variables are independent of others. This independence can be exploited now. I can change the value of t+1 to something else, and I can get new data. This technique of causal discovery allows us to actually augment data. So what you see here is a baseline with 1x real data, and we can keep adding new data. So 1C basically is the same amount of data as the real data set. Then 3C is 3x the new data, and 5C is so on and so forth. And what you see here is that we can achieve performance with 2x or even 3x more data with this simple technique of data augmentation. The same idea, of course, is not only valid on simple Pong games, but robot manipulation tasks as well. So in this case, we see that the object is manipulating 1 or 2 objects in the pushing game, and then allowing counterfactual data augmentation improves performance on state-of-the-art HER algorithm by at least 2x, if not more. So I have about 4 minutes left, and I will probably skip some of the future work, but I do want to describe this work, which we did with Yunzu over at MIT, and Antonio, Anima, and Dieter as well. So what is the question we are asking? So far I've told you that if you had data, you can learn offline RL algorithms. We can do better use of data if we can discover causal mechanisms. In the previous work, we discovered simple causal mechanisms. But what if we want to discover more complex causal mechanisms, such as how a shirt folds? Let's play a simple game. Think of this environment, and what do you think the model is? Maybe a simple ball.
Sure.
Yeah, a simple ball with no damping because the ball keeps on bouncing. Same goes with something like 3 balls, where the balls keep on bouncing without damping. I can play around with this one, and now there are 5 balls. Now this is a challenging one. Try guessing this one. Carefully look at the balls. They change direction midway.
They also seem to go inside each other.
Yes, collisions are turned off.
It's like external forces and no collisions.
Yes. So one could argue that this sort of is slightly trickier to guess because there is an implicit model somewhere which we don't get to observe. So maybe mechanisms which connect these things, which are not just pure collisions. So a simple interaction model will not be able to do this. And we cannot memorize. Why? Because I can change the graph structure of connections arbitrarily. Even in this simple environment, I have 5 by 5, and each edge can have different types and different parameters. So it can be very tricky very quickly. So this is the problem we are trying to solve. Now you can say, of course, but balls are easy. But then I can say, what about more interesting environments where even variables are hard to guess? In balls, at least you know what variables you're trying to guess. So sure, if you want to fold shirts, you need to understand some sort of implicit model. You would argue, but I've seen people doing shirts, and there is a policy that exists. But then I can come back with, say, have you seen pants? And then pantsuits, and then you can say, oh, these are structured things. But then have you seen asymmetric ladies' tops? I do not even know what goes in, what goes out. I do not know how to fold this. I would just hang them or throw them in the basket. So to understand a folding pattern, you have to understand perhaps the stitching pattern. The Euclidean distance between 2 objects, let's say a towel and a pant, may be very similar, but it's the stitching pattern that designs or that guides the dynamics. And that is what we want to capture here. So why bother about causality? So here, what you could argue is, actually, it's easier this way. You can think of an end-to-end model. End-to-end model will model simply just the likelihood. A simple encoder-decoder style model, which is learned with some, let's say, images, image-to-image mapping, can get likelihood, maybe even get disentanglement if you do it correctly, but generalization, questionable. And can it do some sort of counterfactuals? Even more questionable. So understanding causal discovery is equivalent to thinking about an encoder-decoder style model, except where the encoded representation is actually a particular kind of representation, which is an SCM, or structured causal model, which is basically a sequence of DAG, where each edge captures some sort of mechanism. So in this particular case, what we did was, we first of all take visual representations. Visual representations are converted to some perceptual representations that is compact, in this case, key points, which are learned in an unsupervised manner. Then we take these key points and define a summary graph, because this is Granger causality over time. So we define a summary graph, which is basically a single instant in time, a generative model, which captures all of the edges and edge parameters. Once you have that, then you can do temporal rollouts to predict dynamics. And then you can train the model completely in an unsupervised manner, in the sense that you only have observed videos, nothing else. And so first of all, this is just the representation output, where you have input representation and reconstruction is the output, which defines the self-supervised loss and allows us to learn the right keywords. Once we have that, we can apply this to both our simple balls environment, where we will change the edge types and the edge parameters, and then also the fabric environment, where we don't have explicit ground truth to begin. So a very simple use case would be, let's say, 5 balls where you have ground truth. You have the model predict the graph, and what you see on the right is basically predicted key point movements versus ground truth key point movements. As you see, of course, the predictions do diverge after some time. The same idea, of course, can be taken to more number of balls. The interesting thing and the thing to understand here is why this is different, or why this would be different from a simple graph network, is the edges here are also changing. The edges can have parameters. Springs can have different stiffnesses, or rods can have different lengths. So what you see here is you can extrapolate this data on both edge type. Because there is no explicit supervision, you can only establish correlation between length of the spring or length of the rigid relation. And then if you look at just the mean squared error of future prediction, what we see is if you don't do causal discovery, the error grows very, very quickly as you look far out in the future. Interestingly, you can also do counterfactual predictions. So counterfactual predictions would be, you've already observed a data point, and now you go back and change something in that data point. So you see, what if the length of the spring was something else, or what if the edge type was something else? The same idea also allows us to model different types of clothes. So in this case, we were able to model not only a towel, but also, I guess, pants and shirts. While we watch this, and I know we are slightly over time, the thing to understand here is it's slightly different from what people have done in deformable object modeling. One, this is not for one particular instance. We can model all of these objects with a single model. Two, we can handle variations of these objects. So a full sleeve shirt can become a half sleeve shirt, or you can change arbitrary sort of geometries. And in principle, you can also change, let's say, clothing material from, let's say, silk to nylon to cotton, and so on and so forth. And the system will be able to do single shot estimation at test time. So I think because we are out of time, I would skip the part on the safety, but I do want to sort of bring us back to this overall argument that we started with. I think if there's one thing that you remember from this talk today, let it be this. To build practical systems or practical robotic systems, we need to think about understanding what sort of architectures, what sort of structural biases do we need for decision making, not just in robotics, broadly. Of course, robotics does bring its own challenges because of the continuous nature of states and actions. Further, using causality to understand dynamics, credit assignment, reward structure can allow us much more powerful and efficient usage of this data that we collect. And finally, we need to start thinking about how all of these models, when learned from data sets, can be deployed in realistic setups, perhaps under safety constraints. I understand that I did not get a chance to get into safety constraints today, but happy to chat about this. With that, today I talked about work of a lot of my collaborators and colleagues over the years. So I would be remiss if I were not to thank them. And thank you to all of you for being such a great audience. And thank you again for the privilege of your time. Happy to take questions.
A few quick questions.
Sure.
So I think there's some questions on the chat, Animesh.
Let me try to open the chat if I can.
So
yes,
I can read them
I
out.
can look at the chat. Yeah.
Okay.
So Sherry asked, have you tried measuring offline laser performance with out of distribution states? Example, a manipulator arm initialized at a different angle. What happens if the real state falls out of the learned manifold? That's actually a very good question. Yes, indeed. So that is a problem. So if you start very far away from the manifold, there is no way to come back because you don't have the true action space anymore. So in principle, you could have a higher level mechanism where you're switching these action spaces as you go along the task. So if you have zero information about this world, then you should operate in an action space that allows you full exploration. It will be slow, but it will be safe. When you get back to a known environment, then you can explore much faster. That would be the solution to it, but our algorithm currently does not do. Ishika asked, why do you think a policy in representation space doesn't transfer while action space does? Would it be possible to span over more diverse tasks if we bring states to a more common representation to policy to latent states and actions? And would it make both representation and policy transfer? So this is a more loaded question. So first thing to understand was, if you learn the correct representation space, whether of states or actions, what you are essentially doing is think about what is the true objective in your reinforcement learning thing. You're trying to say that I want to move on the gradient of the value function. Whether you are estimating the value function or not, it doesn't matter. Now, the value function implicitly captures dynamics. It has, and it also captures reward model. So for now, let's just assume it's about dynamics. By learning the right representation of dynamics, what you have, at least intuitively, you can think about this is, you have mapped your very hard to explore space into some simple linear space. It can be higher dimensional. It doesn't have to be a contraction always. And in doing so, exploration in this space becomes easy. So that is the value of representation. By the way, another thing that I did not mention today is it would be easier to think about states and actions are essentially as duals of each other because you can flip the model and you can start thinking of them as a singular representation. So it doesn't really matter if you're representing states or actions, it will probably be the same in dynamics because these are just two different subsets of variables in the dynamics equation. Two, you can still learn policies that will generalize, but the generalization of policies is over, let's say, mapping of states and actions to some value. So that function is what you want to generalize, while the representation of states and actions can ensure that the space itself over which your policy is defined is simplified. So you're basically doing this learning in both places, and both of them could in principle be tangential, but we haven't actually done that study formally. Did I answer a question? I don't know. I get very little feedback here. Great. Any further questions?
So I guess if there are no further questions, let's thank Animesh once more for the wonderful talk. Thank you, Animesh.
Thank you. Thank you, everyone, for attending as well.
Yes, I guess Animesh, you have a packed schedule.